An action potential is an electrical pulse that travels down the axon of a neuron, stimulating the release of neurotransmitters, which is how neurons communicate. Hi, I'm Timothy Stokes, and today I'm going to explain to you the science behind the action potential. So you may wonder, the action potential is when a neuron fires, but what about when it's not firing? Well, when action potential isn't occurring, the neuron is in a state called resting potential. During resting potential, the neuron is negative on the inside of the cell and positive on the outside of the cell. This difference in charges is called membrane potential. And this membrane potential is created by sodium ions on the outside of the cell and potassium ions on the inside of the cell. There are more positive sodium ions outside of the cell than positive potassium ions inside of the cell, which creates an electrochemical gradient, which is a really fancy word for the imbalance of charges between the outside of the cell and the inside of the cell. When membrane potential is negative, the cell is considered polarized. The resting membrane potential of the average human is around negative 70 millivolts. That's really small. There are two factors that contribute to membrane potential. The first one is the sodium-potassium pump. It pumps 3 sodium ions out for every 2 potassium ions it pumps in. This is important because it helps establish an equilibrium between sodium and potassium levels. The second are ion channels. There are 2 kinds of ion channels, chemically gated and voltage gated. Chemically gated open up when a specific neurotransmitter binds to them, allowing sodium to enter the cell. And voltage gated only open when the membrane potential is at a specific voltage. So, how does all this produce an action potential? Well, I'm glad you asked. Like I mentioned, the neuron can only fire at 100% or 0%. So, there's a threshold of stimulation. This threshold must be reached for an action potential to occur, and it's usually around negative 55 millivolts in humans. There are 2 ways that this threshold can be reached. The first is when graded potentials, small changes that don't get close to the threshold, combine their strength and shoot through the threshold. The second is when a stimulus is just so strong that it gets right up to the threshold. Now it's off to the races. Voltage-gated ion channels open up and sodium comes rushing into the cell, causing the neuron to become depolarized or more positive. And when one segment is depolarized, it causes the adjacent segment to become depolarized, causing a chain reaction that fires down the neuron. Meanwhile, the sodium-potassium pump is working double time to restore resting potential. So while it's being depolarized, the neuron is also being repolarized right behind it. This is a process called restoration, and curiously, for a split second during restoration, the neuron actually goes below the 70 millivolts and becomes hyperpolarized for a split second in time.